Generally speaking, we can say that the wider a hull is, the bigger the width of the hull is compared to the draft, the more the center of buoyancy B will move sideways when the ship heels over, and hence the more form or shape stability does the hull have. We see here first comparing just a rectangular box here on the left. We heel it over 10 degrees and we see that we lose that volume, we gain buoyancy in that volume, resulting in the B shifting sideways a little bit like that. G pushing downwards, B pushing upwards, and we'll see what happens. A catamaran or a twin hull will have more shape stability than a single hull with the same extreme dimensions, because the B, the buoyancy, will move more sideways in a catamaran than in a single hull, and we will see why. Okay, we have the catamaran, we heel it over 10 degrees, then we see we lose buoyancy there and we gain buoyancy in that volume there. And because these volumes are further out to the side, the B will move more. So you see you get a bigger arm between these two forces. As a result, we see on the single hull we get the GM, a metacentric height about that big, whereas on the catamaran the GM will be significantly bigger. This is because the B moves more. So catamarans have a bigger GM than a single hull, and as a result will make more resistance at small heeling angles. So will make more resistance towards heeling moments. And this makes catamarans very suitable for crane work or using cranes on a vessel. The danger is that catamarans have a G-set curve that extends, that doesn't have a big range. So if you use too much, if you have a too big heeling moment, the boat can flip over, whereas a single hull rarely flips over. GM, as we recall, says something about a ship's ability to withstand heeling moments from 0 degrees heel, but GM doesn't say anything about how much heel the ship can take before it capsizes. When the heeling is more than about 10 degrees, the distance from K up to M will change, and the value of GM really doesn't say anything. To know, if you want to know how the ship reacts at bigger angles of heel, you need to have a look at the G-set curve, the righting arm curve, which you find in the ship stability data. A G-set is the horizontal distance between the vertical line going down through G and the other vertical line going up through the center of buoyancy B. So the distance between G and Z on the figure there. So G, center of gravity, B, center of buoyancy, we heel over, B shifts over to the side, G, the horizontal distance. It's called the righting arm. And we see as the ship heels more over, G-set gets bigger and bigger. The distance increases. Normally it increases until you start to get water on deck. Then the G-set will normally start decreasing. As we see is happening here, we're getting more and more water on deck, and the distance G-set decreases. Now, as long as G-set has a positive value, the ship has an ability to righten itself up towards the equilibrium. Whereas if G-set is 0 or negative, the ship won't righten itself up, and it will either stay on the side or capsize completely. In that case, it's game over. G-set values at different angles of heel can be put into a diagram, and we're going to see how such a diagram is made. We heel the ship over, we see the G-set values increase with the heeling angle, and they keep on increasing until we have the G set, the righting arm, reaches its maximum, typically when you start getting water on deck. When the heeling angle increases more, the G set decreases until at a certain point it is down to 0 again. And from 0 through the top point down to 0 again, we call the range of the righting arm, the range of the G set. When you pass the range, then it's game over. So that is the range of the righting arm, the range of the G set. The bigger picture, GM, says something about withstanding heeling moments and the ship's stability at small angles of heel. Whereas, and if you have a big GM, you have a big resistance towards heeling. Whereas the G-set curve says something about the stability at bigger angles of heel and how much heeling the vessel can withstand before it capsizes. Now, how can we affect the righting arm, the G-set? The further down in the ship that we place the cargo or a weight, the further down the center of gravity G shifts, and hence we have a bigger righting arm. So we see here, we see the G and the Z. Then we shift weights on board so that we lower down the G to G1, and then we have a bigger G set, a bigger righting arm. And the opposite is equally true. If we move weights, cargo high up in the vessel, you have the opposite effect. The G set decreases when the center of gravity G shifts upwards in the vessel. We can also affect the G set curve or the righting arm curve by how much we load the ship. More freeboard means that the range of the G set increases. This is due to the fact that with more freeboard we can heel more over before we start getting water on deck. So, and this again means that the vessel can withstand more heeling before it capsizes. This G-set curve is for a catamaran. It's very steep at the beginning, which means that the vessel is stiff. It has a big GM. It takes a lot of moment to make it to get it to start heeling over. Typically has very sudden, quick movements or rolling movements in the sea, and it also the righting arm has a maximum values at a relatively small angle of heel. This type of vessel is typically known by having a G set that it rises quickly and it also reduces quickly, and the range of the righting arm, the range of the G set, is not very big. You can see here we have a GM of 11.6 meters, which is enormous. Remember that the minimum requirement for cargo ships is 0.15 meters. And we also see that we have a maximum value for the righting arm at 21 degrees of heel, which is a very low angle. Then we have a completely different type of vessel, a shelter-decked, relatively narrow fishing vessel. It's very flat at the beginning. The GM is not so big. This vessel typically has relatively slow, comfortable movements when it's rolling in the sea. But the righting arm increases with the heeling angle, and we can see that it doesn't really, the righting arm curve, the G-set curve, goes to 80 degrees of heel, and the righting arm is still increasing. We can see the G-set, the GM, sorry, here is 0.678. Remember in the previous vessel it was more than 11 meters. This is a fishing vessel. The requirement is that it should have a positive righting arm to at least 80 degrees of heel, and we see it does. If we compare these two vessels, a very wide catamaran with low freeboard, and we compare that to a relatively narrow fishing vessel, the difference in the righting arm, the G-set curve, is striking. The catamaran with an 11.6 meter GM has a very steep righting arm curve with a maximum value at a fairly low angle of heel. whereas the fishing vessel with a much smaller GM of 0.68 has a much slacker curve, but it also, we don't know where it ends because it ends, or it has a maximum value at more than 80 degrees of heel. Even though we cannot say for certain based on these two curves, because the calculations for the catamaran stop at 50 degrees, it is good reason to believe that the catamaran will capsize at a much lower angle than the fishing vessel. The fishing vessel can withstand at least 80 degrees of heel, whereas the catamaran, we see the angle of the righting arm, or the value of the righting arm, is dropping quickly and ends at 50 degrees.